Hello, this is the luckiest maths teacher in the world, and now we're going to take exponential equations a little bit further. Again, the way we solve exponential equations is with logs. We looked at this yesterday, so we had exponential equations like 3 to the power of x equals 27. What makes it an exponential equation is the unknown thing we want to find out. X is the power. So remember, we learned that the way that we could solve this without using trial and error or without graphing was we could write this as a log. So we could write this as x, the power, equals log, and then we write the base, and then the answer. Now, because most of us had calculators that only allow us to do log base 10, even though this here is the answer, to find out what that actually equals, we need to put it in our calculator like this. We put log, and then we put the answer on the top over log of the base. And this is precisely what we put in our calculator. And you should be able to get the answer of 3, because 3 to the power of 3 equals 27. One of the good things, though, about logs is they enable us to solve exponential equations where the number isn't a whole number. We got a nice answer here, x equals 3. We could have used trial and error to find that out. But let's look at another type of example. Let's say we were going to do 2 to the power of x equals 6. Now this one you definitely can't do with trial and error. The answer to this is actually irrational, which means it's a decimal number that goes on forever and ever. It cannot be written as a fraction with integers. So that's why we need logs. So in this case, we just have x equals log base 2 of 6. We need our calculator to help us. So if our calculator only allows base 10, we put in our calculator log 6 divided by log 2. Now when you get that on your calculator, you should get something along the lines 2.58, and it goes on forever like I said. So what that means is 2 to the power of 2.58 equals 6. So that's obviously one we couldn't do in our heads. But let's look at some more complicated equations. So let's look at an equation like this. Now the reason it's a bit more complicated is because it's not just say a to the power of x equals something, but we've also got this 4 here. We've got another operation on the left-hand side besides raising to a power. When that happens, what we need to do is first undo of all that other stuff, and we take the log at the end. So in the example that I've given you, first thing we need to do is divide by 4, because dividing 4 undoes timesing by 4, and then we get 5 to the power of x, and 200 divided by 4 is 50. So now we've got what we want. We've got just something to the power of something equals something else, and we can use logs as the way we did before. Now it's very important that we follow this order of operations. It will not work if you don't do that. So then, of course, we need to take the logs. So x, whatever that number is, will be log base 5 of 50. That's the answer. It's an irrational number. You can leave it like that if the question says exact form, because this is the answer exactly. Or if it says rounded, we need to use our calculator. So again, we put in our calculator log 50. Your calculator does log base 10 of 50 divided by log 5. And the answer we get is about 2.43. So we know we're right, because what it's saying is that if I exchange x for 2.43, then this statement here will be true. Now we know that 5 to the power of 2 is 25, which is less than 50. 5 to the power of 3 is 125, which is obviously more than 50. So we would expect our final answer would be somewhere between 2 and 3. So similarly, if you have a question like 3 minus 2 to the power of x equals 33. We do the same process as for linear equations, so we're going to subtract 3 from both sides. So we get minus 2 to the power of x, 33 minus 3 is 30, and then I'm going to divide each side by -1, and I get 2 to the power of x equals negative 30. Now, as I explained to you yesterday, not all exponential equations have a solution. This one here has no solution. So I put D and E for does not exist because you cannot raise 2 to any power to get a negative number. So this one does not have any solution. If you tried to put it on your calculator, you would get an error. So please be aware of that. So I'm just going to do one more question, which is a bit more problem solving, and then we will be done. Okay, so let's have a look at this question here. A person invests $5,000, it grows 6% per year, and how long before this investment doubles? So what that means is the person originally, so I'm going to call this Y0, year 0, they invest $5,000. After the first year, this has grown by 6%. So 6% of $5,000 is $300. So after year 1, their investment has added $300, so it's $5,300. Then at the end of year 2, I take this amount and I increase it by 6%. So 6% of $5,300 is $318. So this will now be $5,618. So then I could do the same again and again. What you will see is that it's increasing by an increasing amount. So if I take 6% of 5,618, it increases by $337.08. So this will become 595508. So here, it increased by 300 there, it increased by 318, and it increased by 337.08, okay? So I could keep going and going until I see the investment double, but exponential equations allow us to solve this a lot quicker. And this is a very, very important application of exponential equations, compound interest. So the hard part about this is setting up the equation. So what I want to do, if I want to find out how many years this takes to double, I need to find an equation that tells me how much the investment is worth after so many years. So I want an equation that tells me that it's worth $5,300 after year 1 and that it's worth $5,618 after year 2. So this is the way that you build up equations like this. So I'm going to call A the amount that's in the account. So he started off with 5,000. Now what I'm doing is I am increasing this by 6% per year. So you probably learned this in year 9 when you were doing percentages, percentage increase and decrease. The way you increase something is by multiplying by 1 plus 6 over 100. Okay, what I'm doing that is I'm multiplying that at the end of each year. So to go from year 0 to year 1, I've multiplied 5,000 by 1.06. To go from year 1 to year 2, I've multiplied 5,300 by 1.06. So it's just repeated multiplication. So what I'm doing is I am multiplying 5,000 by 1.06 a number of times. The number of times is equal to the number of years. So the amount after the first year is 5,000 times 1 plus 6 over 100 is 1.06. What I'm doing at the second year is I'm taking the amount after the first year and I'm multiplying that by 1.06. But of course, the way I can write this, because there are two 1.06, is 5,000 times 1.06 to the power of 2. Now, at the end of the third year, I'm taking the amount at the end of the second year and I'm multiplying by 1.06 again. So this is how much after the second year I multiply by 1.06. And that is, of course, 5,000 times 1.06 to the power of 3. So the amount after n years in this account is 5,000 times, and to make it easier, I'm going to write 1.06 in here. So it's 5,000 times 1.06 to the power of n, where n is the number of years. So that is the hard part. So now the question tells me how long before the investment doubles. So I'm being asked, what's the value of n when A, the amount in the account, is equal to 10,000, which is double what it started with. So this is my equation. I want it to be worth 10,000. And that equals 5,000 times 1.06 to the power of n. So I use exponential equations just like I did in a previous example. So first I have to get rid of this because I want this thing by itself so I can use logs. So I divide each side of the equation by 5,000. Okay, and what I end up with is 10,000 divided 5,000 is 2 equals 1.06 to the power of n. Okay? So this is precisely where logs come in. This is just like all the other ones we've done. So I write this in logarithmic form. So I write log, the base is 1.06 to the 2 equals n. And I put that on my calculator. So then, of course, what I put on my calculator, because it only does base 10, is log 2 divide log 1.06. And the answer I get, and you should get, is approximately 39.52. We need to round that up. So it will take about 40 years for this investment to double. So there are some questions that you need to do like this one, but it's exactly the same. Set up your equation just as I have done. You won't need to do all this stuff. This was just me explaining it. Set up the equation like I've done, get everything over to one side, and then use logs. Please let me know if you have any difficulties. Other than that, this has been the luckiest maths teacher in the world. Have a great day.